yet another attempt to correct the auto grader. What happened initially was that something changed with the move to Julia 1.0, where the output that was being produced, even if your code was perfectly correct, didn't match the supposed correct output in the script, simply because the way it was printing out had changed. We decided to try one way, and by using rootint there, so it wouldn't put like the main dot rootint and so on. That had some of you noted that actually had the awkward side effect of what it meant is to make it work, you'd have to feed in something other than your code as the parameter to the script, and you'd have to give some other Julia file, and it created a mess. So we decided to roll that back, put that back so that now you do pass it as a parameter, and then we just updated what we expected correct output to be. So when you're running your own tests, you shouldn't see the main dot kind of thing. And then that was the main reason we tried to do it, so that what we list as the correct output should be the same as what you see if you run it yourself. Now it's not quite. If you run it yourself just from the console, you'll see something like rootint.binop. When you run it through the auto grader, the way that it's set up, it will actually generate something that says main.rootint.binop or main.rootint.numnode. And so that's the only difference then between what you should be seeing and what the auto grader actually is expecting and looking for. The most important thing is that when the TAs go to run their full version of the auto grader, that what your code is producing matches what they're looking at. We did not change the assignment though. If you've already turned it in, great. If you're working on it, great. You don't have to change anything. As long as you're following the assignment spec and producing correct output, the TA's grading script should work accordingly. We just try to provide these little proto-graders just so we can try that out ahead of time, or that you can double check and make sure you're returning the right stuff. But as long as you're returning the appropriate abstract syntax tree, or from parse, or number out of calc, or for a few of them throwing an exception when you correctly detect that there's an error in the user's input, your code should grade just fine. And please let us know if there's a problem with that. Any questions? Sorry about the confusion. We're just trying to the move to 1.0 kind of changed a few things for us, and we're still trying to make sure that we're compatible with it. Hopefully now we've learned and we shouldn't see these issues with Interpreter 2 or Interpreter 3. So Interpreter 1 is due tonight. Interpreter 2, pardon me, the next one is due the end of next week. So it's not this weekend, but the end of next week. That actually has the nice benefit, this was not planned, but it actually means you have nothing due over conference weekend, which I hope gives you time to do that. I won't take credit for that, that was not planned, it was just part of the feedback from the previous, from winter semester was, and I'll say this just to give you a bit of a heads up too. Yeah, Interpreter 2 is a bit more than some of the others, and we could really use some extra time on that one. Or the students in the next semester should probably be given a little more extra time on that. Well, that's you, and so you're getting a little more extra time on that. Interpreter 2 is one of those where once you understand it, the amount of stuff that you have to write in code is not extensive. Much like this first assignment, are most of you finding that your time is spent understanding the interpreter that's already given, and then once you actually understand that, the changes are straightforward?
Yeah.
Okay. Well, straightforward might be watering it down too much, but that the bulk of it is understanding and less on the actual implementation. In general, that's my strategy. If you've been in my other classes, I like to design assignments where if you understand the core concepts, doing it's pretty straightforward. It's not thousands of lines of code. But that if you don't understand, doing it's almost nigh unto impossible. So that's just my assignment philosophy. I try to make it where the focus is on understanding and less on spending a lot of time writing huge amounts of code. That is a good thing, a good skill to have, and we put you through that in other classes. All right. So any questions on anything so far? All right. So I had hoped that my hope going into today was that by the end of today, we would have enough that you could get started on the assignment. In the first section, we almost got there. It was enough that I was able to talk through in English some parts that we're going to do in Calc. So hopefully we'll get to a point where maybe with some additional reading of the code, you could get started. If not, on Wednesday, we will definitely go over everything else and even spend some time diving into the assignment itself more. All right, so let's dive in and do that. So let's kind of recap how we got to this point. I feel like this is the beginning of an episode of Supernatural, right? The story so far. Right. Remember, we started, yeah, you can tell my TV viewing preferences. We started with a very simple calculator, really. We just worked with arithmetic expressions, numeric literals, plus and minus. That was the CI0 interpreter. Then we said, all right, let's look at the process if we want to add more to it, and in particular, we added a conditional, if 0. And so what we saw, the flow was, start with an example, what do you want it to look like, then define that concretely in syntax, then take that concrete syntax and figure out what the corresponding abstract syntax would be, then extend the parser so that that concrete syntax would be recognized and produce that abstract syntax, and then introduce a case into Calc for handling that new piece of abstract syntax. So that's the flow. That's what we've done every time since then. Then we said, all right, let's use that idea and let's add variables to the language. Now the big conceptual jump there is if you're going to add variables to the language, and so we did this with, where we could define a local variable and then reference it. The big conceptual takeaway from that is as soon as you start having variables, you have to have some place to store what the value of a variable is. Now that might seem kind of funny because in every language you've used so far, it's the compiler's job to worry about storing what that variable is. I just declare the variable, I give it a value, and that's the compiler, the interpreter's job. Well, like I said a couple times, you're down on the other side of that wall. You're the one making the interpreter or the compiler. So you have to build data structure that stores this variable has this value. And we called that an environment. And we extended, made changes to all the calc functions so that code doesn't execute in a vacuum anymore. It's no longer enough to say, calculate the result of this expression. We have to say, calculate the result of this expression in the context of this environment, which has a whole bunch of variables defined. So an environment stores, this variable has this value. We didn't talk about it as much when we were going over that, but if you're doing this with a compiled language, what happens is that instead of saying this variable has this value, because you're not going to know the value until runtime if it's the result of some other computation. Instead, in a compiler, you build a similar data structure that says, instead of this variable has this value, you say this variable lives at this address in memory. And that memory address contains the value of the variable. We're going to come back and talk about that when we talk about sort of mutating data or modifying state. This data structure in a compiler is called a symbol table. So if you've ever heard the term before, that's what a symbol table is. It stores this variable lives at this address. And that address, by the way, is very often, if it's something that's on the stack, this offset off the stack pointer. So it could be a relative addressing. Usually symbol tables also store other information, like and it's this type, and it's cons or not, it can be written to or not, and other kinds of information you may store about the variable. So that's where we're at so far with it. Let's now add user-defined functions. So what you've seen is that if you want to build in your own new operators, hopefully that's pretty straightforward. The question comes in now, let's allow the user to find their own functions. And what we're going to see is that there's a couple key pieces that we're going to have to change besides just the more straightforward part of the implementation. All right, so let's get to it. First off, what do we want? You have to remember, you start from the outside. What do you want this to look like to the programmer in the language? So let's build anonymous, first-class, user-defined functions. So remember the terms we used before. Anonymous, it's not going to have a name. That means you can give it a name later, or you can store it, or you can pass it, or use it right away, or whatever, but it will be created anonymously. And then also it's first class. So it's going to be like any other value in the language. It's just a different type. So far our interpreter has numbers. Now it's got numbers and functions as its types that it can return. So then you have to define, all right, what's the syntax for that? Let's just simply borrow from what you saw before in Racket. Let's use the keyword lambda. By the way, there's nothing magical about lambda. It's chosen in Racket for historical reasons, actually originated from Lisp, for historical reasons dating back to the lambda calculus. And that's just the character that Alonzo Church and others working on this stuff happen to use. Okay? You guys have already figured out by now, right? Mathematicians have this fetish with Greek characters. So that's because you run out of all the regular ones, right? And so you start making up other ones. That's solely the reason for it. If you wanted to, you could call this proc, you could call it func, you could write out function, you could use the keyword fun. I've seen all those used in different languages before. Doesn't matter. We're simply saying here is a function definition, and the keyword we're going to use is lambda. Now in Racket, you saw that we would put the formal parameters in parentheses like this. We're actually going to simplify it a little bit. Just to keep it simple, let's just start off with one parameter functions. And then we'll move on to multiple parameter functions. So just in sort of a milk before meat kind of a thing, we're just going to start simple, one parameter. So if there's only one parameter, we don't really need to put parentheses around it. So keyword lambda, the name of the formal parameter, and then some body, which is a body expression. Sorry, some body expression, not somebody. Right? An expression to execute when this code is called, right? When this function is called. Bit of terminology here. Remember, we've talked about this before. The name that you call the parameter when you define the function or declare the function is called the formal parameter. Okay? So think of this in C++. When you write a function, or Java or whatever language, when you write a function and it has parameters, you give those parameters names. Those are the formal parameters to the function. It's how the function inside of its own body refers to, in other words, the code of the function. It's the name that it uses to refer to its parameters. But when you call it, we're not going to pass x. We call it x here, the formal parameter, that's how we use it here. But we're going to pass in something like 3 or 10 or 42 or whatever your favorite value is. That's said to be the actual parameter. Right? It's the parameter you're actually using when you do the computation. So formal, what you call the parameter when you declare the function. Actual is what's the value you're actually passing when you call the function. See the difference? Okay, so I'm going to use that terminology throughout the semester, actually, and already have been. So that's what we want it to look like. Now, I can then take that. Remember, this is created anonymously. This creates and returns a function. To introduce functions into a language, you actually have to introduce two new pieces of syntax. One, what's the syntax for declaring the function? And two, what's the syntax when you want to call the function? So this is what it would look like to create the function. We need to have a way of calling the function. And we're going to do it kind of Racket style. open paren, an expression for the operator, another expression for the actual parameter. Notice I say actual parameter singular just because, again, we're just going to work with exactly one parameter functions, just for simplicity. So this is created anonymously. I can use it right away, or I could give it a name. I could do something like this. I could say with f being defined to be all of that, call f with 5. I realize it's kind of weird syntax. This is just the syntax for our OWL language so far. I can create it anonymously, find a name to it, and then reference it by its name. And notice this is how you call functions. Here's the operator, and this is the actual parameter, or sometimes called the operand. Okay? We could do it this way, giving it a name, or we could also just do this. Oops. Formal, and all of this, body. But we can just simply write this. So this is one expression where this is an expression defining the operator, the function to be called, and this is the actual parameter. Got it? All right, so that's what we want it to look like. Let's write it more concretely in BNF. So open paren lambda, a single identifier for the formal parameter, the one formal parameter, and then the body can be any arithmetic expression. Okay, so lambda, formal, body. The other piece that we have to add is a function call. And this will simply be any arithmetic expression and any arithmetic expression. So notice syntactically I said any arithmetic expression. So that's syntax. Semantically, what has to be true about these expressions? What have they better evaluate to?
One better be a function, the other better be a number.
Yeah, this one had better be a function, and this one had better be, yeah, whatever, yeah. Now, since we're not going to type our functions, we're not going to worry about types, but we are introducing a new type in the language. So this could be a number, or it could be another function. Right? We can use this to write higher order functions. So these two are what we're adding now in class interpreter number 3. Got it? All right, let's turn to the code then. So you'll notice that as we've been adding things, remember we start with an example, define the concrete syntax, define the abstract syntax, extend the parser. All that's pretty routine. It's kind of automatic where you should be able to start looking at the concrete syntax, figuring out what the corresponding abstract syntax would need to store, and then extending the parser accordingly. Remember I said that it's so kind of automatic that there are tools that will actually automate the process for you. When we talk about Lex and Yak or more modern Antler. So I'm just, in the interest of time, I'm going to skip ahead. I've already put in the abstract syntax in the parser, but let's look at them. So remember, we have an arithmetic expression. Sorry, I should have explained. This is not a symbol in BNF. This is, our grammar has grown so large, I don't want to write it all every single time in class. So this is, an arithmetic expression is all those other cases we had, plus these. So here are all these other cases. A numeric literal, plus, minus, you're extending that to these more general binary operators. An if, a with, a reference to a variable, and now here are the two new pieces. So it can be, remember we defined two pieces of syntax. One is for a function definition, the other is for a function call, or what is generally called a function application. So if you think of it like math, it's you're applying a function to operands or arguments. So we'll call this a function application. So we have one type of node in our abstract syntax tree for function definitions. That stores the name of the formal parameter as a symbol, and it stores this body, which could be any other arithmetic expression, any other piece of code. And then for a function application, remember we have two expressions, one of which, so remember, syntactically they can be arbitrary arithmetic expressions. Semantically, so we'll just label these meaningfully by looking at the semantics. This is first one will evaluate to the function to be called. The second one, the arg expression, will evaluate to the argument or actual parameter to be used. Got it? Okay, I realize I'm doing a lot of talking, and so please jump in with questions. Questions up to this point? All right. Then let's look at the extending the corresponding changes in the parser. Well, you'll notice this case just comes in as yet another parenthesized expression where the operator is lambda. So we just add another case. If it's a parenthesized expression, which is going to come in as a Julia array, we go through our is it plus, minus, if, or with, is it any of these, and then is it the keyword lambda? In which case, we just return a function definition node that stores the unprocessed just identifier here. We don't try to apply a separate production to get here. Just store the identifier and parse this body expression. Now, notice then there's an else on this chain. So if it's a parenthesized expression, the first symbol had better be, or the first thing had better be the symbol plus, the symbol minus, the symbol if zero, the symbol with, the symbol lambda. Else, what we had before was if it gets to that point and it's not one of those, then that is some unknown operator, and we threw an error accordingly. Now though, if you look at the grammar, it's this case now. Sorry, have I written this too low down on the board? Can you guys still see? Even those over here, I know the podium kind of blocks it. Can you still see this? Okay. So we're going to, now, if it's a parenthesized expression and it doesn't contain one of those built-in operators, the assumption is it's a function call to one of the user-defined functions or operators. And so we simply build and return a function application node, and we store the result of parsing the function expression and the result of parsing the argument or actual parameter expression. So those are the changes to the parser. What that looks like then is when we lexically analyze the same case I wrote on the board, this is the sequence of tokens that come in and their structure with the sub-expressions. Here is the abstract syntax tree coming out. So for this expression, this parses as a function application, where this is the function expression and this is the arg expression. So the function expression is a function definition with formal parameter x and all this parsed for the body. And then the actual parameter or arg expression is the numeric literal 5. So everybody okay on what's coming out of the abstract syntax tree? Or out of parse in the abstract syntax tree that we're going to feed into calc? Questions at this point? Okay, so everything so far has been syntax with hints at what the semantics should be. Now we need to actually code the semantics. So we'll code the semantics in calc. We need a new case of calc for handling what if they define a function, and a new case of calc for when they call a function. So let's start with this first one. So So you're going to get a function definition function definition node. It will store, it's one of these. It stores a formal and a body. The formal is just a symbol. The body is some already parsed expression. Let's just start from the output and work backwards. What should this return? So it's a function definition, but it's going to make an anonymous function. Right? What do we return? Okay, a function. Now, all the functions you've written, when you go back to what I've said before, all the functions you've written are, you write a function, right? It's right there, it's a function. I coded a function in Python or C++ or Java, and the compiler interpreter handles that. Remember, you're on the other side now. Right? So when we say we're going to return a function, we have to actually return a data structure that represents user-defined functions, a function in this language that our programmer's writing in. Not Julia, but OWL. Okay. So let's come up with a data structure for storing functions. What would you need? So you're processing a function declaration, not a function call, function declaration, and it's going to return a data structure representing that function that it just created. What should go in there? What might you want to remember?
The name of the function and what you're supposed to
Okay.
do.
So if you're defining them with names, then it would include the name of the function. What would we store instead of the name of the function? And this might be what you actually meant to say. The name of the formal parameter or formal parameters for the function. So we need to store this function definition node. Says, oh, this is, its formal parameters have these names. Let's remember that. Okay. The body is this expression. That would be good to remember too. So let me ask you a key question. What do we do with the body of the code? When we encounter this function definition in calc, do we do addition? Why no? Or how many of you would think maybe yes? So why no?
Well, in the case of this body, it would be addition, but we're going to use that body in an environment that we create for this function, correct?
Right, at what time?
Only when we call this function.
When you call the function. So notice when you declare a function, you do not execute one single lick of code within that the body of that function. Right? You just simply package it up and remember it. In the case of a compiler, you compile it and store it somewhere. What you do though, or when you execute the body of the function, is when you call the function. So think about this in C++. When you write a function, and again, substitute Python, Java, any language you're used to, when you write the declaration of a function in C++, and the compiler is going through and encounters that declaration, does it actually execute code within it? You wouldn't expect it to, right? You're just saying, here is a declaration of a function. Remember this function so that when I call it later, here's what that is. So we're going to do the same thing. When you call the function, we'll execute the body. But for now, all we're going to do is we're just simply going to remember. So we're just going to remember the user said they wanted to build a function that has this formal parameter and this body. Sure. We'll just store a little data structure that says that formal parameter, or multiple ones if that were applied, and this body code. You see the idea? In fact, we can actually just store this same thing. So we're going to store an internal data representation of a function is going to be nothing more than storing, remembering what was the formal parameter when in the declaration, and what was the code or body of the declaration. Now, if you're doing this in C++, you might remember other things like what's the return type and what are the types of the parameters, but we're just working with a fairly simple one right now. Everybody okay on that idea? So processing function declarations does not execute the code. It just packages it up for calling later. All right, now we're going to come back to that in a moment because it turns out it's not quite that simple. But just conceptually think of it that way for now. There's one more thing we're going to have to also remember. What happens now when that's the stored function declaration? What happens now when you call a function? So let's think of the function call. If this is the function, and the argument or actual parameter here is this expression, what are the sequence of steps that you want to do? What's the first thing you might want to do?
Calculate the length expression, turn that into.
Yeah. So what happens is this is actually an expression. So I'm going to need to calculate that first. So I'll recursively call calc on the current, on this function expression. Oh, by the way, in what environment do I calculate that in? What environment do I pass to calc when I calc this expression? Yeah, just whatever the current environment is. All right, so you calculate this one and you get back a internal representation of a function. Remember, it stores the formals in the body. What do you do next? Remember, this is coming in as this, this piece of abstract syntax contains 1, 2 sub-expressions, right? We evaluated this. What's next? Evaluate this one too. So evaluate the formal or the expression that should semantically return a function, and this is where you can check and make sure, did this evaluate to a function, not a number or something. Evaluate the function expression, evaluate the arg expression to get the actual parameter. Right? Both of those are in the calling environment. All right, now what? What do we ultimately want to do when you call a function? Right, apply that function to that value. But what does it mean when we say we actually apply the function? Eventually, what does that mean? So I hear some saying some of it. What? Can you say it louder?
Calculate the body.
Right. Ultimately, calling a function means, remember, we didn't execute the body of that function before when it was declared. When you call a function, ultimately we want to actually calculate or evaluate or execute the body of the function. So ultimately, we want to execute this code. Right? Now when we're executing this code, we're going to run into a variable reference x. So let me ask you this then. It's going to go look for that x. Where's it going to go look?
In the environment.
In the environment, right? So, but that environment had better have x in it. So what do we need to do before we evaluate that?
The environment for the function to evaluate.
Right. You need to make a new environment. So notice the steps here. Once we've executed these two, so this part here evaluates to a function. This part evaluates to the actual parameter. The next step is build a new environment that binds the formal parameter of the function to the actual parameter, and then within that, execute the body of the function so that when you encounter a variable reference to the formal parameter, it knows that, oh, that x has this value 5. You see the idea? And that's exactly how we're going to code it. Questions so far? Because we're about to take a turn with it. So questions? You feel like you understand it so far? Just sort of at least, I realize we're kind of hand waving and talking through in English first. Okay, turns out there's one other thing we're going to have to do. What if this body of the function contains a variable reference that's not the formal parameter of the function? Where are we going to go we're going to still look in our current, the environment that binds x to phi. We're going to look there, and we're not going to find it. By the way, those are said to be free variable references, or free variables. So what did we do when we did for our environment? When we encounter a variable reference. If it's not in the current environment, we're looking at the parent environment. And then up and up, right? So that raises an interesting question. So let's just go back to basic bracket. We're going to find y to be the variable 3. F is a function, so y has the value 3. F is a function that takes a parameter x and adds x and y and returns it. Okay? Really simple. But let's go through and look at the variable references. This x is the actual formal parameter here. These are what are said to be bound variables, or at least within the context of the function itself, it's bound. Because I can say, oh, that references that one. What about y?
Because you need the y that was defined.
Okay. Now, most of you are going to say, why are you even asking? There's only one y on the board. Does everybody agree this y should reference that y? Okay. Now, suppose I did the following. Let's define a function called g that takes a formal parameter named y. Now there are two y's on the board. Now, we're going to call f, we're going to pass 0 for x. Okay? And then, let's call g and pass 4. So let's trace it through the execution. I'm going to call the function g, that's this function. I'm going to pass 4 for the actual parameter. So the formal parameter y gets 4, right? So this y is 4. And then I call the function f. Well, the actual parameter I'm passing to the formal x is 0. So this x is now 0. And so clearly, that gets passed in there, right? And this 4 got passed in here. Pardon this sort of John Madden-esque kind of a drawing. All right. So now we get to the body. We're going to add x and y. Well, remember we said we passed the 4 for y, so y equals 4 when we call the function. And so when we're inside the function, x is 0 and y is 4. Right?
It's an arbitrary decision.
Answer is actually yes. It is an arbitrary decision. But the reason we're talking about it is you're the language designer. As designer of a language, you get to make that arbitrary decision. So hopefully it's not so arbitrary. Hopefully it's well reasoned. So we're going to think through why you might choose one or the other. So does this feel right to you when I say that that y is 4, and so when I add 0 and 4, I return the result is 4? So some are nodding. Okay, I'm trying to be persuasive with the argument. Some are shaking their head. So I gave an argument for why it should be 4. Anybody shaking their head want to give an argument for why it's not? Yeah.
In the case of f, that y shouldn't know about the y that we created when we defined the function g. It should only know about the previous definition of y.
So here's what he's saying. At the time I wrote this function, this stuff didn't exist yet, right? So this free variable y should refer to the y that was, and maybe there's some other stuff defined before that even have y values, but it should refer to the one that was in scope at the time that I actually processed or created this function. Now down here, the argument is, yeah, that's all well and good. At the time you made the function, y was that. But at the time I call the function, y is 4.
Shadows the outer y.
Well, it's not even, it does shadow it within here, but the question is, should it shadow it within here? So here's the fundamental question. Notice the way I was phrasing it. Do you use the value of the free variable y that's in scope at the time the function was created? Or do you use the value or the variable that's in scope at the time the function is called? Do you see the difference? So it's a scoping issue. Does this y refer to this one or to this one? This is the y that was in scope at the time the function was created. This is the y that's in scope at the time the function is called. Both are valid choices. Almost